Hi Al, I hope you're doing well today. So we're going to work through the Chapter 8 practice problems, but before we do that, I did want to give you a quick overview of Markovnikov versus Anti-Markovnikov and kind of what I recommend for this chapter. So the biggest thing for this chapter is you're starting this what's going to become a trend in your OChem 2 where you learn about a functional group, you learn how to create it, and then you learn how to react it forward. So those are going to be kind of what we're doing in Chapter 8. So you learned how to make alkenes in Chapter 6 and 7 with elimination reactions. You learned which alkenes, about the properties of them, which alkenes would be more stable than others. You learned how to get Hoffman versus Zaitsev, that sort of thing. And now we're going to learn how to react to alkenes forward. So how can we react to alkenes forward? So first of all, a basic addition reaction with alkenes, you need to look for Markovnikov or anti-Markovnikov regiochemistry. And what regiochemistry means, where does it add? So stereochemistry is like how is it arranged, and regiochemistry is does it add to carbon 1 or carbon 2, and how can you tell that? So if you have an alkene such as this one, sorry, that's a methyl group, it looks weird on here. I have bad handwriting. The first step is going to be this area of electron density. The alkene itself has a lot of electrons, will attack and get this proton because it's, slightly positive and this slightly negative. There's a dipole movement here. So this is slightly positive while this is more negative. So it's going to attack, and then this bond will break, and you'll end up with a carbocation. So you'll notice that I drew the proton adding here and the carbocation here. The reason for that is because this carbocation is more stable than over here. So this is going to be naturally where the carbocation goes. And that's a Markovnikov addition, where you see the nucleophile attack and add at the position of the most stable carbocation. So you'd get something like this. And that hydrogen's still there, it's just implied. Anti-Markovnikov would be if you had this kind of product and it added with the nucleophile adding on the place where the less stable carbocation would form. So I know that's not super intuitive, but you would get that with if you have peroxides or some other things, conditions will make things add anti-Markovnikov, and otherwise, for the most part, things will add Markovnikov. So that's kind of an overview of what we mean by Markovnikov or anti-Markovnikov. And I usually just abbreviate it by saying Mark and anti-Mark because Markovnikov is a long line. And so that's about regiochemistry. You'll also need to pay attention to some stereochemistry and some stuff like that as we go through these reactions. So the next thing I want to talk about is adding what's called adding water across a double bond. So if you have water, H2O or HOH, and you add it across a double bond, what that means is you'll get an H on one side and an OH on the other. That's called adding water across a double bond. It's also, you can just say you're creating an alcohol, however you want to say it. But there's three main ways to do that. So one is acid catalyzed. One is called Oxymercuration Demercuration. I am just abbreviating it Oxymerc Demerc because Oxymercuration Demercuration is hard to say. And then one is Hydroboration Oxidation. I think it's useful for you to know these. You definitely need to know the names. It's useful for you to also know the mechanisms, especially of 1 and 3, because they help kind of explain some things for you. But just quickly, I'll go over the highlights. So for acid catalyzed, usually you'll have a double bond like this. If it's an asymmetrical, that's when you get the Markovnikov versus anti-Markovnikov. And then some kind of acid and water, so you get a hydronium ion. So you'll get the area of electron density will attack, and you'll end up with a carbocation here. It follows Markovnikov regiochemistry. And Oh, well, I guess I won't get quite to that yet. So you'll have a carbocation and a water. Well, the next step is this nucleophile will come and attack. You have to be sure to look out for rearrangement. In this case, the most stable carbocation formed, but if maybe you had something nearby that was more stable, that's a possibility. After the water adds, you get a structure that looks like this. The proton's already added here. This is positive now, and it'll have to undergo deprotonation, probably by water or something else in solution. A base, like a water or something like that, will come and take it, and you'll end up with an alcohol. So you've added water across a double bond. You added H2O. Okay, so that is acid catalyzed addition of water across a double bond. There's Markovnikov regiochemistry. It can undergo rearrangement, and this stereochemistry is you'd get a racemic mixture because of that carbocation. It can, just like an E1 reaction, it can attack from the top or the bottom. So you're going to get a mixture, a racemic mixture of R and S configuration. Okay, well, now what if you want to do this and you don't want to have rearrangement? That's what oxymercuration demercuration is for. So oxymercuration demercuration, it's a two-step reaction technically. So you'll see the, let's see if we have that, just that same double bond. I drew it kind of crazy this time. With these, no, the two's on the outside of the parentheses. These reagents, it's a two-step reaction. So you'll see this first. And then the next step, it looks like this. Be NaOH or KOH or some kind of OH minus. So after the first step, you're actually going to end up with your OH added. Well, here, let me draw it like this. So basically what happens is this crazy triangle forms with this group, and I think it's worth it for you to look over the mechanism, but I don't think it's worth it for me to take the time to draw it for you right now. So basically you're going to get your something that looks like a triangle forming right here between these. You'll have your OH added here, and on the other carbon you'll actually have part of this mercury group. So the alcohol adds first, different mechanism, and you get your mercury here. So this is the oxymercuration. We've added oxygen and mercury. Hg is mercury, and the demercuration is the NaBH4 and NaOH, and that's going to replace it to give you your hydrogen here. So it adds differently than your than your acid catalyzed, but it still gives you Markovnikov regiochemistry. I think it also gives you an uncontrollable stereochemistry. I think it can be a mixture as well. And then it has no rearrangement. So that's how these two are different. So if you have a molecule where a rearrangement is possible, but you want Markovnikov addition with no rearrangement, you'd use oxymercuration demercuration. And then last, you have hydroboration oxidation. For whatever reason, this one's my favorite. I just like it. So if you have the same molecule, it's also going to be sort of a two-step process. You're going to add BH3. Sometimes it shows up differently than BH3, but that's the main thing you're looking for is BH3. And actually it forms like sort of a box, and it adds in a fashion where the H is going to go to one side and the BH3 is going to go to the other. So it'll form something that looks sort of like this. So after your first step, you actually end up having an H here and a BH, actually that's a BH2, not a BH3, BH2 here, because this is BH2 with an extra hydrogen bonded to it. And then your BH2 will be replaced. This is your hydroboration step. Your oxidation step is H2O2 and NaOH or some kind of OH minus. So that's your oxidation step, and it'll replace your BH2 with an OH. So if you'll notice, that added in an anti-Markovnikov fashion. So it added anti-Markovnikov and actually gives a syn stereochemistry. So basically, if this was a wedge and dash situation, both your hydrogen and your OH would be wedges or dashes, unlike the racemic mixture of the other one. And there's no rearrangement. So these are kind of the big ways to add water across a double bond. They all create an alcohol. You can tweak these slightly, both instead of having water, you can have alcohol. And then instead of adding OH, they'll add OR, whatever your alcohol was. So that's ethanol, they'll add 2 carbons. If it's methanol, 1 carbon, whatever it is. And that's kind of the big things for this, I would say. There's other kind of reactions in this chapter. So if I were you, what I would do is make a chart where you have the alkene, the reagents, any the product it'll form, and any special considerations. So that would be like anti-Markovnikov, syn, or anti, that kind of thing. So for example, you could be like alkene plus H3O plus, any kind of acid will give an alcohol across the double bond. It adds Markovnikov, racemic mixture, and it will undergo rearrangement. So that's what you have to look out for. Then you could do the rest of them. You could do hydroboration oxidation. You could do oxymercuration demercuration. You could do, later on in the chapter, we'll have Br2. So you could have Br2. That's going to add bromine across the double bond, right? I think it adds anti. Well, I can't remember off the top of my head right now. Let me double check. Don't count my word for it. I have it in my notes. I just wrote it down. I always forget that. And that's also helpful to know. If there's something that you consistently forget, then yeah, I think it does add anti. So you could write that. If there's something you consistently forget, take note of that and pay special attention to it so that you remember it for the exam. So this adds anti, and it adds in the Markovnikov fashion, which doesn't come into play if they're the same, but if you have Br2 and OH, it does come into play. And that gives you a halohydrin that is Markovnikov. It would also be useful for you to have the mechanism. That's something I would probably also add, just so you kind of know the idea of how it's formed. I think knowing mechanisms is a lot easier than just memorizing things, because it can help you understand the flow of the electrons and why things happen, and it's just easier than trying to memorize everything. So that's kind of my advice for this chapter, is to make yourself a study guide, basically, where you can organize all the reactions and have an easier time making your way through all, like sort of wading through all the information that's being thrown at you, which is kind of what happens in this chapter, and a lot of the later chapters are like that as well. Okay, so chapter 8, practice problems. Markovnikov addition of HI to 2-methyl-2-butene involves. So 1, 2, 3, 4, 2-methyl-2-butene. Actually, so that's the one that I've been drawing. This is a good one because it's asymmetrical. So HI, so I'm going to go through the mechanism. This bond will break, and you're going to end up with a carbocation right here, and the proton added here. And then the I- is going to come and attack, and you'll end up with an iodine there. So I believe that's the process. Now, what are our options? Initial attack by the iodide ion. No, we see that the initial attack comes from the alkene, so that's not true. This is basically the same one, but it's the improper iodine instead of iodide. Iodide atom, iodide ion, or iodine atom. So those are kind of your options. None of those make sense. Isomerization of 2-iodo-2-methylbutene. Now that's something that I feel like I don't even know what that means. Isomerization of 2-iodo-2-methylbutane. Isomerization into what from what? That's not something we've even talked about. So I think that one's just throwing that in there to trick you. So then our options are D or E. Well, 2-methyl-2-butene, the carbocation forms at 2 because it's Markovnikov addition, not at 3, and 2 is more stable. So the right answer is answer choice D. Okay, answer 3. Question 3. Treating 1-methyl cyclohexane with HCl would yield which of these? Okay, so let's draw it. 1-methyl cyclohexene. So I'm assuming the double bond is right there at the methyl for the cyclohexene. That's the only thing that makes sense to me, since they don't specify where that's at. So we're going to have the same thing where the alkene attacks a proton and Cl- is formed. So if the proton adds here, the more stable carbocation will be formed here. And then the Cl- could come in and attack. So that is my best guess at the right answer. And I would assume that this actually would be a racemic mixture. So it'd be, a wedge and a dash plus it's an enantiomer. Actually, no, I made a mistake. This isn't a stereocenter. Do you know why? It's because if you go around the ring, there's a plane of symmetry in the middle. And actually, these two things are exactly the same. So there aren't even 4 different things attached to it. So we don't need to draw the wedge and dash. That was a mistake I made. So answer choice C would be right. It's the same structure. I just drew the 3D one, which was not necessary. Okay, so next question. What would be the major product for the following reaction? I think here is where we're going to start to see rearrangement come into play. So you have HBr. Same thing's going to happen. The alkenes attack. This bond breaks. The hydrogen is going to add here. We're going to have a carbocation left behind here plus Br-. But the carbocation is going to rearrange. So let's talk about rearrangement. Rearrangement occurs if you have a carbocation. So you need a carbocation, but always look for this when you have a carbocation. And then on an adjacent, so it has to be next door, carbon, there has to be a more stable option. And it's going to undergo what's known as methyl shift or hydride shift. These are the only two things that could happen. Either a hydrogen can move over or a methyl can move over. Sorry, I didn't realize this wasn't on the camera. So either a methyl can move over or a hydrogen can move over, and that's it. So let me give you an example. If you have a carbocation forming right here, it would be happier and more stable here. So this methyl, I call it being a switcheroo. Really what happens is the electrons move over, but it just basically trades, and then you're left behind with an absence of electrons. So the positive charge is here and the methyl moves over. So technically that's what happens. I think of it, though, as more of just a switcheroo. It's just easier for me to think of. So that was able to happen because there was a methyl group there. Now, if instead you had this situation, the carbocation would not be able to move over because you don't have a hydrogen or a methyl to trade places with it. All these, you've got a propyl, what's that, a butyl, and an ethyl. So none of those can trade over. You need an available methyl to trade over. So this would not undergo rearrangement. Now let's do another one. If you had this structure, this carbocation would undergo rearrangement. The whole methyl wouldn't need to shift. Just the hydrogen could trade places. So you'd end up with a carbocation that looks like this, and the hydrogen would have moved over here. So you can either do a switcheroo with an adjacent hydrogen if it's a more stable option, or an adjacent methyl if it's a more stable option, but that's it. It's not going to do any other switcheroos, really. So in this case, we have a carbocation here and a methyl and a hydrogen. available next door. So the hydrogen is going to move more easily than the methyl. So we're going to get a switcheroo. And I'm not going to draw the implied hydrogen there because you guys should know it's there by now. This hydrogen will move over and the carbocation will take its place. So, and you'll notice I got rid of the wedge and dash. That's because if it's sp2 hybridized, like carbocations are, it's going to be trigonal planar. It's going to be flat in the plane of the page. So things can attack from the top or the bottom of it in this instance. Now your Br minus is going to attack. And it's going to have stereochemistry again, but because it can attack from the top or the bottom, it'll be this plus its enantiomer. So the right answer here should be answer choice C. This just has the bromine adding down at the bottom. This had, again, both of these are actually the same answer. This plus its enantiomer, I guess. So neither of those is going to be your right option because your carbocation didn't rearrange. And this has an Anti-Markovnikov without rearrangement, so that wouldn't add in this form. So your answer is answer C. Okay, for question 6, which are the possible products of the following reaction? So same thing, your alkene's going to attack and this bond's going to break. And you're going to end up with the hydrogen adds here and the positive charge adds here. Now again, you always have to look for rearrangement if there is a possibility and there is an available hydrogen next door. So these two are going to switcheroo. I'm not going to draw that implied hydrogen because it's implied. This hydrogen takes the place of the carbocation, and now there's a positive charge on the other carbon. Okay, when this bond broke, it also generated Br minus, so the Br minus will then attack. Rearrangement happens really fast, so that would have happened first, and then you'll get your bromine added. So the bromine will be a wedge or a dash, and the other thing will be the opposite because when it's trigonal planar, something can attack from the bottom or the top. So the right answer would be, it could be a wedge or a dash. You don't have to draw stereochemistry though because there's a plane of symmetry right here in the middle, and these going around the ring are exactly the same. So technically the right answer is answer choice C. Now I want to draw your attention to something here. A lot of times I would get questions like this wrong because I would have looked at this and thought, oh, that's answer B, and circled it because I wasn't paying close enough attention. So sometimes when it's a little wonky, I'll circle the structures with their answers or draw a line between the structures and their answers so that I know I'm getting it exactly right. And that's just kind of a way to slow down and make sure you're not speeding through the problem. Okay, number 7. This is Oxymercuration Demercuration. And I love these two problems together because they show you the benefit of oxymercuration demercuration over the acid catalyzed addition. So if you have an acid catalyzed addition, you can have rearrangement. If you don't have an acid catalyzed, if you use oxymercuration demercuration, you'll still get the Markovnikov product, but you won't have it undergo arrangement. So it forms this crazy triangle. When the double bond here attacks the mercury. So I didn't go all the way through the mechanism. I'm just going to show you quickly. It like attacks. Then this comes back and attack. This bond leaves and you get this crazy triangle. You don't really need to know why. I just focus on the triangle itself. So this forms. And then the water in the second step, I guess it really isn't the second step. It's more like the second half of the first half because it's the water that's from here is going to come and attack. And remember, it's going to attack at the same position that would form in the same place it would attach if it was a Markovnikov carbocation where the carbocation would form. So right here's the more stable. And then this bond breaks. So this is complicated. I don't know that you need to know every step of this. I think it's helpful to see so that you know why it forms the way it does, but not necessary. So then you have OH2 plus that gets deprotonated. And then in the next step, part 2, B, NABH4, and NaOH come in, and you definitely don't need to know this part, but they basically replace this big mercury structure with a hydrogen, and then you've got your OH and it's deprotonated. So that's kind of the overall. I don't know if that's more confusing or not. I think it's helpful to see it worked out, but don't feel like you have to be able to regurgitate that exactly. I think that triangle structure helps me see the Markovnikov addition a little bit easier, but if that's confusing for you in this case, I think it's okay to just go ahead and choose to just know that it forms that way. So this is the structure you're going to get. You don't have control over the stereochemistry, so it is going to have both a wedge or a dash, like that, plus it's an enantiomer. So this is the right answer. And this is one that tricks me. I would have circled A on this, thinking like if I was going fast, I would have just thought that was part of the above structure. But the right answer is actually answer B, the one with the OH as an enantiomer. So that you got to look out for that. That's not a great reason to miss a question on an exam, and one I have absolutely done before. Okay. Question 8, what is the major product of the following sequence? So the first one, you should recognize that pretty easily. We've got an alkene and an HBr. So it's going to attack. Seen it a few times now. And this one's interesting. The proton will add here, and you'll have a carbocation. It can't rearrange because that's too far down the line. It can only rearrange if it's right next to it, a more stable structure. So that won't undergo rearrangement. It will just end up with this structure. So that's part one. The second one is NaCN and DMSO. So if you are thinking, I don't recognize this, there's no alkene, I'm not sure what to do. The thing I always do is go through all the types of reactions you learned. So you've learned acid-base reactions. CN minus is pretty basic, but CN minus, but there's no proton available. There is a leaving group. So if you have a strong nucleophile and a good leaving group, then we're dealing with SN1 or E2, basically, because of strong nucleophile. So this is a pretty narrow nucleophile, and this is secondary, so it could go either way. In the absence of heat, I'm going to go for a substitution. So I think this CN minus is going to come in and attack and kick that bromine out and end up with CN here. Now in this step, because there's a carbocation, you have bromine as a wedge and a dash. So when it gets replaced by a CN, that means a CN will be a dash and a wedge. So the right answer here would be whichever one gives you that one. I think that is that none of these choices? I guess so. That's kind of tricksy for them to give you none of these choices, because this has two CNs. That's not possible. The chlorine didn't get swapped out, so there's no leaving group, so that wouldn't work. This would have only worked if you had an anti-Markovnikov addition, which isn't possible if a carbocation forms. This is an elimination, which maybe would have been possible. That definitely would be a side product, but I think the major thing would be a substitution. So I think the answer to the major product would be answer choice E, none of these choices. That's tricksy. Okay. For question 9, which is the major product of the following reaction. Okay, so again, if you're like, wait, this isn't an alkene reaction, we're in chapter 8, I'm not sure what's going on here. You just got to look at what you have. There's not an acid-base possibility. This is basic, but there's not an easily available acid. So then the next thing we learned was SN1, SN2, E1, E2. Well, this is strong, so it's going to be an SN or an E2. And this is a big bulky base, so I'm going to go with an E2 with a Hoffman product. So it's going to do the less substituted product. So this base is going to come, steal this proton, form a double bond, and kick this chlorine out to give you a double bond here. And then you're going to add HBr for your next step. So that forms the hydrogen adds here and the carbocations here plus Br minus. Anytime there's a carbocation, you got to check for rearrangement. There is a methyl available right next door. There's not a hydrogen available, so it won't do a hydride shift. It'll do a methyl shift. So this methyl will just do a switcheroo. Again, that's not the most proper way to think of it, but that's how I think of it. And then the Br minus is going to come and attack. I didn't draw that hydrogen there because it's implied. Once you've seen where it adds, I don't think it's really necessary to keep drawing it. So you've got your bromine adds here, and it's going to be in a racemic mixture. It could have either side, a wedge or a dash form because it's from the positive. So your right answer would be, looks like answer choice C. Because you've got, they drew it a little bit differently than me, but on carbon 3, you have a methyl and a bromine, and then on carbon 4, you have, Okay, so answer choice C. Let's move on to question 10, which would be the product of the following reaction. So this is weird, it's a bicyclic ring, but try not to worry about that too much and just focus on what you know. Don't let that freak you out. So this is addition of water across a double bond. It's acid catalyzed, so there is going to be a possibility of rearrangement. The proton is going to attach here to make the most stable carbocation possible. And then the water that you have left behind is going to attack because it's got extra electrons, so it's going to fill that in. So, but it has two H's. So when those electrons form a bond, it is going to be positive. Remember that hydrogen was added here. I'm not going to draw it again because it's implied at this point. And then this will get deprotonated probably actually by another water in the solution. It doesn't really matter a ton. When you have things like this, a lot of protons are just moving around because these have such similar pKa's. But you'll end up with OH here and an H here. So that looks like answer choice D. Okay, for question 12, Hydroboration Oxidation. I don't know why, this is my favorite. It makes the most sense to me. And I like that it's different. It's the only one that does Anti-Markovnikov. Okay, so when the BH3THF, I just think of that as the BH3, and when it lines up, it needs more room for the BH2, and the hydrogen is going to go here. So that's your BH3 structure. And sort of what's going to happen is a bond will form here, and a bond will form here. So you end up with a hydrogen over here and a BH2 over here. Now this bond is broken, and it formed this new one, and this bond is broken, and it formed this new one. And then in the second step, the H2O2 NaOH, you don't need to worry too much about how, but that BH2 will be replaced with an OH. I almost wrote OH2, but it's just OH, just an alcohol. So this is my favorite one just because it's easy to keep track of, I think. You see the hydroboration oxidation, and you know it's going to be the Anti-Markovnikov, and there's no rearrangement, and you don't have to worry about anything. You basically are just throwing that OH on at the end, and I think that makes a lot more sense to me. So the right answer is going to be, this one's tempting, but it's not Markovnikov. And also remember these add in a syn addition, so not that it matters in this case, but both of these would be wedges if that mattered for this question. This isn't right because it adds two alcohols. This didn't add an alcohol at all, and we haven't seen carboxylic acids be added. This one, it's tricky, but they basically just flipped the right answer backwards, so answer A is the right answer. Okay? So if you ever see something like that and you're like, wait, I don't see the right answer, which is kind of what happened to me just then, eliminate what you can, and then you'll be left with the right answer. So eliminate what you can based on what you know. Which is the major product of the following reaction sequence? Okay, well, this is not an acid-base reaction because there's no easily available proton. So that has to be an S and 2 and an E2. There's no double bond, so it can't be any kind of addition reaction. It's probably going to be an E2 because the strength of this base will take it to the 2 side and the heat will take it to the elimination side. So that means it can steal, well, it could steal a hydrogen from here, or it could steal a hydrogen from here. I think it would probably go with a more stable hydrogen, is my guess, the Zaitsev product rather than the Hoffman product, because this is more narrow. So the base is going to come and steal that, form a double bond. Sorry, that's an arrow. This pin kind of drags. And the leaving group will leave. And you're going to end up with a structure that looks like this, the double bond right here. The next step is BH3THF. So they helped you out. 2A and 2B, that's the 2 steps of hydroboration oxidation. So that means we're going to add Anti-Markovnikov, so the alcohol goes to the less substituted side. A water and a hydrogen added over here. With the hydroboration oxidation, because of the way the BH3 sets up, they add as both wedges or both dashes. And you can go back to the last question to see the mechanism for that. I'm not going to keep doing the mechanism every time for this one because it's too complicated. So, okay, so they do this, I think, to mess you up. But they have one with 2 wedges here. That's not the right answer because the hydrogen needs to be a wedge, not the CH3. So if you're looking between this OH and the CH3, one's a wedge and one's a dash. For the OH and the hydrogen, they're both dashes, but this is a CH3, not the hydrogen. So the hydrogen that's in there is also a dash. So answer choice C should be your right answer. Okay, what is the major product for the following reaction? This is another hydroboration oxidation. So we're just going to add water across the double bond here. The OH is going to go to the part that's less substituted, and it's going to be a dash or a wedge, and so is the hydrogen. And this other substituent is going to be a wedge. So A is wrong because there was not a hydrogen added. This opens the ring. We have not learned anything about opening rings yet, so don't get crazy. The OH here doesn't work because these are both dashes. Same thing that they did to trick you on the last question. You need a dash and a wedge for the existing substituent. The hydrogen and the OH need to both be dashes. So the only possible right answer is answer choice E. D just has no stereochemistry at all, and the OH added the wrong one, so that doesn't work either. Okay. That would form if you did Markovnikov addition. And with rearrangement. So even without rearrangement. So if you ever want to kind of practice, make sure you fully understand, it does help to go through and say why all the other answers are wrong. Okay, here we go. Oxymercuration Demercuration. I'm not going to go through this one again because we did go over it, the mechanism already, but I do want to point out, instead of the thing that's attacking it being alcohol, the thing that attacking, or being water, the thing that attacking is alcohol. So when we have that triangle form where you've got the mercury and where the double bond used to be, and you're going to have something attack, instead of water being what attacks, what's going to attack instead is an alcohol. So one of these is going to be an R group. So that's going to mean instead of adding water across a double bond, you're adding alcohol across a double bond. So the OH going where the most stable carbocation would be here. There's no rearrangement in this case because there's no carbocation actually forming. It just goes where the carbocation would have been based on Markovnikov. And instead of OH forming there like it normally does, you're going to get OET. And then the hydrogen will be the other one. So the right answer for this one should be answer B. So this is anti-Markovnikov addition. This is with rearrangement. So if you were to do an acid catalyzed, and this is something we haven't even talked about yet. So, and here This one, the first time I worked through this, I always work through the practice problems before I work through them for the video to make sure I know what's coming up and what all we need to talk about. And I circled E the first time because that is the product of oxymercuration demercuration with water as a solvent. So this is tricky. If this had said H2O instead of ethanol, this would be right, but it's not right. So be sure to look out for that on the exam. That's one that consistently gets me. Okay. So for question 17, this starts with hydrogenation. It starts with a poisoned hydrogenation, though. So this we talked about P2, Lindlar's catalyst. I think this is technically Lindlar's catalyst, but this is a poisoned hydrogenation. So what that means is you're only going to go from a triple bond to a double bond. It can't hydrogenate all the way down to a single bond. So we talked about that in the last chapter, so go check that out. So it'll go from a triple bond to a double bond. So because it's no longer a triple bond, so it's not sp hybridized, it's not 180 bond angle anymore, it's 120. I'm going to change the bond angle. And if it mattered, in this case it doesn't, it would be cis, but these are both hydrogen, so it's the same either way. So that's the first step. And then the second one is just hydroboration oxidation. So we'll have the BH2 would add here, the hydrogen would add here, because the BH2 needs more room is how I think of that. So it becomes the OH and the H. I'm not going to go through the whole mechanism because that's just takes a lot of time, but I usually draw it like that to remind myself quickly of the mechanism. And this is the structure that you'd end up with. So it looks like, is that answer choice E is the right one? Yeah, they just have the bottom part of this going the different way, but I think it's the same. And then 1, 2, 1, 2. Yeah, so answer choice E should be the right one. So answer choice B would be if you had done oxymercuration demercuration. That's how you'd end up with answer choice B. Or is that C? Did I get it? D would be if it went all the way to catalytic hydrogenation, if it wasn't poisoned. C would be if you did Markovnikov with oxymercuration demercuration. B is something we haven't even talked about yet, and honestly, I had no idea how you'd get A unless you had some serious rearrangement. Oh, I guess, yeah, it just would be if you start with this structure, the rearrangement would happen. So that's how you get all of those. Okay, so question 18, what is the major product of the following reaction? Okay, Br2 and CCl4, we haven't talked about this. Br2 adds across a double bond, and I believe they add anti across a double bond. So we'd get a bromine added to each side. And then here we have the NaNH2 and excess NH3. So you have to ask yourself, is this going to be an acid-base question with this NH2 here? No, because there's no easily available protons. So then we have a strong base, we have two good leaving groups. So actually this is going to be an elimination reaction. So NH2 is going to come, steal a proton, and kick this bad boy out. But then you still have this. So NH2 actually can do that again. It's going to take one of these protons and kick out your bromine. So you'll end up with a triple bond here, but then you still have excess NH2. So it's actually then it will perform an acid-base reaction, and you'd end up with this negative charge there. But that actually, then we add acid, and the acid adding is what takes it back to this. So the right answer should actually be answer choice B. Now, if you only had one of these NH2s, it's possible that you could get this, but the bromine would still be there. This is a possibility, but with excess NH2, it's going to keep reacting. So you just have to account for that continuing to happen. And NH2 with excess NH3 on a terminal alkyne will always deprotonate it to turn it into a strong nucleophile. Okay, what's the major product of the following reaction sequence? So this is another poison catalyst, and it's going to make it cis instead of trans, but it's going to stop at the double bond. And then we're going to add Br2 along it. And these BRs, I believe they add anti. Yeah, I think they do. And so we'll have a bromine added here and a bromine added here. That should be right. Let me count my carbons just to make sure. 1, 2, 3, 4, 5, 6. So I think your right answer would look like this, and that is answer choice B. So A is if they add with syn stereochemistry, and C and D don't have 2 bromines adding, and E has too many bromines adding. It doesn't account for this first step. Okay. What would be the major product of the following reaction? So if you do Br2 in the presence of water, what you're going to get instead is what's called a halohydrin. So instead of just adding your 2 bromines like this, you're going to get a Br and an OH. So, and that's called the halohydrin. So the right answer for this question should be answer choice 1. So these don't add anti. These doesn't account for the solvent. This one doesn't account for the bromine. It's just adding 2 alcohols. Same thing. What's the major product from the following reaction? Okay, so here's something that matters about these is it acts as Anti-Markovnikov. And Br2 actually acts as the electrophile. So this attacks and kicks this out. It's actually more complicated. It forms a similar triangle to what you saw with it looks something like this. It's similar to what you saw with the Oxymercuration Demercuration. And then this is a strong partial positive, and this is a strong partial negative. It's kind of confusing. I think of it as this breaking up and basically following the same mechanism as an acid catalyte. So it's not the most proper way to think about it, but it's how it makes sense for me to think about it. So that means you're going to get your bromine added here. I do this all kind of crazy. Once this is added, your bromine will add to this side, and you'll get a carbocation over here. Then the OH will come in and attack. That's not exactly right. It's not the right mechanism 100%, because that doesn't account for the stereochemistry, which is an anti-addition, and in this case it wouldn't be. But it does account for this being added to the less substituted side in the style of Markovnikov, which is what happens. So you do get anti-stereochemistry. So if this is a wedge, then this is going to be a dash where your OH adds, and this is going to be a wedge where your Br adds. So if that was confusing, you can ignore it. It's not the proper form. This triangle forming is the right thing, and that can explain both the anti-stereochemistry and the regiochemistry, but I always think of it more in terms of this because I always forget which side the bromine adds to first. In this case, the bromine acts as an electrophile, and the other side, the more substituted side, is where the alcohol is going to add. So in that case, the right answer choice should be, I guess that would be answer A. This doesn't have a bromine added. This they add syn instead of anti. This they don't, and they add Anti-Markovnikov, which is not right. This is Markovnikov, but they add syn, and this is Anti-Markovnikov and syn, so it's double wrong. Okay. These two are actually the same wrong answer, I think. Yeah. If that happens, it's probably not the right answer. Okay, 22. KMNO4 with H2O cold and dilute is going to result in adding alcohol across a double bond. Hot KMNO4 will cleave a double bond and oxidize it, but we're going to talk about that in a later chapter. And I believe these add syn, so they both will be wedges. So the right answer should be answer choice C. So that's just one of those to put in your chart that you're going to make at the beginning of this chapter and memorize. They're both going to add syn. Okay, now osmium oxide with pyridine and these specific reagents actually ends up doing the exact same thing. It's going to add 2 alcohols across a double bond, and they're going to add cis. So the right answer is answer choice A. For 24, what's the major product from the following reaction? KMNO4 with heat actually cleaves a double bond. So I'm going to draw this kind of crazy. So we had a double bond here, right? And I drew it as if this broke. And I know all these bonds are proportional, whatever, but I want you guys to be able to see what happens. So you just can think of adding an oxygen in here. Now, KMNO4 is a really strong oxidizing agent, so it's actually going to continue to oxidize. My box got kind of crazy. I forgot how I was drawing it. It's going to continue to oxidize this aldehyde down to a carboxylic acid, but it's going to keep the same number of carbons. 1, 2, 3, 4, 5. So it's the same number of carbons, but it's going to basically just break apart a double bond and put 2 oxygens there. And with KMNO4, it's going to keep oxidizing any hydrogen all the way down to carboxylic acid. So the final structure I'm going to straighten it out now. This is carbon 1, arbitrarily, not based on IUPAC naming standards. Carbon 4 also has a carboxylic acid there. And on this side, it didn't. 1, 2, 3, 4, 5, 6. It didn't go all the way down to a it has a ketone there, not a carboxylic acid. It doesn't go all the way down to a carboxylic acid because there's an R group on either side. There's no hydrogen that it can, right here we just had an R group and an R group. If there had been a hydrogen there, the oxygen can force its way between an oxygen and that, or between a carbon and hydrogen, but it can't force its way between 2 carbons. So then the right answer will be whichever one looks like this. So that should be, that has 2 carboxylic acids, so that's not right. This didn't break the double bond, so that's not right. This has these in the wrong places. So it only could be D or E, but E didn't oxidize fully, so it must be answer choice E. Okay. Addition of hydrogen chloride to the following molecule would produce what? So this is a stereochemistry question, basically. As long as you know the double bond attacks, you're going to have a carbocation form here. The hydrogen will add here. It's going to undergo rearrangement, so it's going to become this, and then the Cl minus is going to come in an attack. Oh, I'm crazy. I turned that chlorine into a CH3. You can ignore all that. So sorry. Here we go. I'll start over again, and I'll actually draw it right this time. Oh, my pen's running out of ink. Okay, I'm actually going to draw it right this time. So you have a double bond and a chlorine here. I knew it was a stereochemistry problem, and then I made it a rearrangement problem. So this attacks and breaks, and you get your carbocation right here. No rearrangement will happen because that's a chlorine, not a methyl. And then your chlorine will attack. So because this is a carbocation, your chlorine can attack from the top or the bottom, which means you'll get both your chlorine as a wedge and your chlorine as a dash, but it won't do anything to this other chlorine. So both answer choice 1 and 2 are correct. Technically, answer choice 3, oh no, because it'd have to be flipped around. So 1 and 2 are correct. This one would only be right if the chlorine that was a dash was on this side, because then you'd just be basically looking at this molecule from the other side. These are both wedges, so that doesn't make sense again, unless you'd flipped it around and the chlorine was over here. And then this just has the chlorine added to the wrong spot altogether. So the right answer should be answer choice A, 1 and 2. Sorry for the initial confusion. Even I can be gung-ho about something and then just make a mistake. And that's why it's really important. I'll see sometimes students will draw their hydrogens like this. But if you do that, you might think they're methyl groups like I just did and mix yourself up. So I'm sorry for the confusion. Okay, question 26 is how many stereoisomers are possible? So let's see. Let's go ahead and just draw it out here. CH2, the double bond between them, CH2, CH3, and then you've got HBr. CH2, CH2, CH3, and then HBr. So initially you'll get the hydrogen add over here and a positive charge on this side, and then the bromine can attack. So the bromine can attack either as a wedge or a dash. It can go from the top or the bottom. So I'm going to say there are 2 stereoisomers possible. Okay, 27 looks like it's just a repeat of 25, so we'll skip that. Now, what is the chief product of the acid catalyzed hydration of 2,5-dimethylhexene? So let's draw it. 1, 2, 3, 1, 2, 3, 4, 5, 6. 2, 3, 4, 5 dimethyl 2-hexene. Okay, if it's acid catalyzed, hydration means adding the water. So adding water across a double bond, you'll end up with the carbocation will form here and the hydrogen will add here. And then you're going to add, the water will attack. So it looks like you should end up with. So this is tough because it's checking you on if you know how this adds. It's also checking you to see if you know the nomenclature system. So it's kind of tricksy. It's checking you on both. So once you have this structure, sorry, I'll move it up some. Then we go ahead and name it. So let's see. 1, 2, 3, 4, 5, 6. So it's still hexane. 2-methyl, 5-methyl, so that's 2,5-dimethyl. So I'd say 2,5-dimethyl, and you can say 2-hexanol, or you can say 2,5-dimethyl hexane 2-all. Either of those is correct, and we've seen both of them. IUPAC is moving more towards this, but these are still also correct. So then I would say the correct answer should be answer choice B. Okay, we're getting towards the end here. Question 29, what is the major product for the following reaction? So this adds this oxymercuration demercuration of water, so it's Markovnikov with no rearrangement. So if you have Markovnikov, the alcohol is going to add where the more stable carbocation would have formed, but with no rearrangement. So in this case, your alcohol should add right here, and the hydrogen would add here. If it was acid catalyzed, you would experience rearrangement, but you're not in this case. So the right answer should be answer choice D. And you will get a mixture of the alcohol as a wedge and the alcohol as a dash. This would be, if it was hydroboration oxidation, that would be right. This, same thing, hydroboration oxidation. This would be just KMNO4 that's cold, and this would be with rearrangement. Okay, and then question 30. What is the major product from the following reaction? Okay, so again, we should have the same thing. It should add with Markovnikov with no rearrangement. So the OH is going to go where the most stable. Ooh, it's not an OH. There's CH3OH. Okay, that would have gotten me. That's the same thing I talked about. So the OR, or the OH, is going to go where the more stable carbocation would have formed. We're going to get rid of this double bond, and the hydrogen would go to the other side. I'm not going to draw out the mechanism for you guys every time, because I did that at the beginning. It just takes a little bit longer, and we're already at an hour, so the OR adds to the more stable configuration of the carbocation. So the right answer would be answer choice D. If I was taking that on an exam, I think I maybe would have chosen answer choice C and gotten it wrong. So gotta look out for that. If it were me going into the exam, I'd write, look for alcohol on oxymercuration demercuration to make sure I don't make that mistake. Okay, well, I hope this was helpful for you guys. If you have any questions, please feel free to reach out.